Hi everybody. At the conclusion of our last tutorial, we were able to apply a mesh to our cover part, and we also specified an injection location. Now this was done to conduct an initial filling analysis. We have run the filling analysis. Now let's check our results. You'll come over here into the study tasks panel, and you'll find under the results that they have been populated within the flow folder. So let's take a look at one of the most important results, and that's the fill time. This tells us whether or not the part filled. We have a time scale here, which goes from 0 to the end of fill, which in this case is 1.19 seconds. Let's take a look at the part. We can go to Home, click on Results, and we can play an animation of the filling. So we can see that the part fills completely, that all four corners of the part have filled. It is not a short shot. However, the filling is not balanced. And what I mean by that, if you take a look at the part as it's filling, let's stop right there. You can see this end is filling a little bit sooner than this end. That's not ideal. And the reason that is we've offset our gate from the center of the part. This is a symmetric part, so if we wanted a symmetric fill, we would have had gated right here at the center of the part. We did this on purpose, and this was because I wanted to show you on a later tutorial what the effect of gating is on part warpage. Ideally, we like the part to fill uniformly. This will result in a decrease in part warpage. So now that we have a pretty good idea that the part's going to fill, we can proceed with our more thorough simulation setup. Uh, Basically, we did this early on in order to determine whether or not we're going down the right path. If we gated here, there's a longer flow length, the part might not have filled. So now that we're fairly confident that the part's going to fill, we can start to add more detail to get a more representative simulation and more representative analysis results. For example, one of the first things we're going to need to do is to actually model the melt delivery system or the runner system. This cone here is not how we're going to be injecting material into the molds. This was just done because we didn't have the time to specify a runner system, and we wanted to quickly and easily validate this design. But now we're going to need to add some more detail, and that's what we're going to focus on in this tutorial. We're going to learn how to model a runner system. So we can go back here. And this is important because what we have here is we have pressure, and this pressure is not accurate because it does not take into consideration the runner geometry and the gate geometry. The gate geometry is a key factor in determining the pressure that it takes to create this part, and that's because the geometry has a lot of influence on the viscosity of the polymer and how easily it will flow through the mold. So if you have a very uh, large gate, it's not going to shear the material, and you might have higher pressures. Whereas if you have a smaller gate, you're going to get a lot of shear, and that's going to lower the viscosity of the material, and you might have a lower injection pressure. Nonetheless, we're going to have to determine that, and that's done by actually modeling the runner system. So, but before we do that, I would like to change the color scheme here because I don't find this particularly uh, attractive. So I'm going to go here to my new nodes in the layers, right mouse click, go to display. I'm going to select and change the color to something that I like. I'm going to do the same thing for the triangle as well. Go with something different. Okay, and you can there's a lot of basic colors that you can choose here. And you can actually go into the whole spectrum here and choose whatever color you'd like. You could define custom colors. There's a lot of ways that you can customize the software to your likes. In this case, I'm just going to pick something off the palette, and There we go. That I can work with that. So we'll turn the nodes off here. I'm going to keep the injection location that I specified, and that's because we're going to uh, take a look into how an unbalanced fill results in part warpage. So keep the node, the cone there. In order to create your runner system, go to your Home tab. Within your Home tab, go to the Geometry menu. And within the Geometry menu, you'll see a Create submenu. Within the Create submenu, you have a Runner System wizard. Go ahead and click on that. And my advice to you is that this is going to be an iterative process. Go through the process once. It's going to generate a melt delivery system for you. If you don't like it, you can come back and you can change it. So let's go through this first iteration together. And we're going to keep the defaults. The default settings are based on where the part is in space. So we're going to keep the default settings here, but we can specify the sprue position, or we could specify the hot runner position as well. In this case, we're not going to use a hot runner because it's a smaller part and we don't need to. And we also have our parting plane. The parting plane is where the two halves of the cavity and core, they meet together to form the mold. So we're going to go ahead and keep our default conditions, and we'll step through the tutorial. It gives us a default sprue diameter and also a runner diameter. So let's keep that. And finally, it gives us our gate. And we're going to keep the defaults in this case as well. Let's see what it gives us. Create a copy. Oh no, look at that. So we have our sprue here going through the part. We have the gate where we would like it. Yep, we'd like the gate to be right there at that point. However, this is going to be problematic. This is not going to be a very good part. Tooling wise, I don't think this is feasible. So let's go back into our runner system now. We're going to go into our runner system, and we're going to move the sprue out in the positive Y direction. So right now it's 37.5 in the Y direction. For example, let's take a look at it this way. So this is our sprue. We'd like our sprue to be out here. So go back into our runner system. It's 37.5. Let's put it at 150. So 150 is going to take it to the left in the positive Y direction. And let's just step through it again. Let's see what happens. As you can see, it's moved the sprue out to where we would like it. Now this, you might say, well, this runner is a little bit too long. It's a little bit too long. That's not a problem. We can go back into the runner system wizard here. We can go 100. And it's much closer to the part. And you might take a look at this runner and you say, well, this little portion here, why can't we just make it straight? So let's try to do that. We come in here, we'll measure from here to there. It's about 10 millimeters. So we need to shift the runner in the positive X direction by 10 millimeters. So go back to our runner system wizard here. X, 110. Go to next, next, finish, and there we go. Now we have our sprue, we have our runner, and we have our gate. It's fairly straightforward, pretty easy, and we have a much more representative model of how this part would be in the actual mold. And now our results would be even more accurate because we've modeled the sprue, we've modeled the runner, we've modeled the gate, and we can actually measure the shear and the heating and the whole flow dynamics as the polymer melt is entering the mold. Okay, so now what we're going to do again is we're just going to run the results, and we'll have a much more accurate and much more representative result simulation that we can work with. Thank you very much. Bye.